Okay. Today we're talking about the last thing that's on exam one. So, and we'll probably talk about it today and tomorrow, but we'll start it today. And the topic of centroids, that's the last type of problem that's going to be on exam one. Exam one is next week, so make sure you don't forget about that. Let's see. A couple of things before we start. Here's, well, that's quarterly. Here's an example of little truss that would qualify based on our equation yesterday, or well, last time, about the number of moments, or number of members, and number of joints, and degrees of freedom type thing. This one would be statically determinate, but it would qualify as the unstable. So it's got the one part in the center there that is not triangulated. So if you have trusses like this that are unstable, you might could pin them down the way you support them in the real world. You might could bolt them to stuff that kind of makes them indeterminate because of the reactions you've applied to them, or that we haven't necessarily talked about. But here's what I mean by unstable, is that these little triangulated parts cannot change shape, but you got this kind of action that can happen when there's an untriangulated part. So that's the unstable part. And then you think, and you try to rationalize in the real world, well, a bridge wouldn't do that in the real world, but that's because, maybe these two reactions at the end where you have it supported are more than what we're modeling as pin, and one of them being a roller. They might be more than that, and that increases the number of external reactions that this truss could have if you thought about, well, those two ends are bolted down to something that's not going to move, and then the truss can't move up and down like this because this piece is bolted to something. But that is not what we're actually analyzing when we put a pin at one end that has two reactions, and this idea of something like a roller at the other end that only has one reaction. So that's the unstable part, or unstable part, is that I can't move, the triangular shaped pieces, they don't actually change shape. It's just I can't move this one at all because this piece right here is fixed. But that's the kind of thing that we're talking about. Now I've got it all kinds of crazy. I don't know if I can, there it goes. All right, so that's what I'm talking about with how truss may be unstable as far as method of joints or method of sections goes. You have this idea that it could change shape relative to what it started as without any of the pieces actually stretching or bending or breaking in any way. And that's what that equation is telling us, that it could do that. Particularly, it could do that based on the types of reactions we're given at the supports. Kind of related to that, at least in the idea of reactions and supports, is this problem. So this one looks like it's not determinate. It is statically indeterminate. If you counted up all the members, and you have two pins, a pin at E and a pin at G, so each one of those adds two reactions. So in your equation, you have M plus 4 has to be equal to the number of joints times 2. And this one wouldn't qualify. This one would show up as statically indeterminate because of the extra reaction at pin G. The trick, I don't know if you want to call it a trick, but the thing that's going on here is at pin G. So if we drew I'm not going to draw the whole truss out, but let's draw enough of it to get the idea here. So you've got, in general, what's this thing look like? Looks like this. So you've got this kind of truss, and then you've got a pin here at, I think that was E maybe, and then there's a little member coming off, and there's a pin here, and that one's at G. And you've got some forces, I don't even know where they were. Let's put some forces on here. All right, so this is not the truss that we actually have, but it's similar to that. And the key here is that all truss members are two force members. So if we look at GH, so member GH, that's This guy at the bottom right there. So there's a pin at G, but if I look at member GH, its free body diagram, if I draw the actual member, there's G, there's H. It either has to look like this, well, I want that to be red. It's in tension, or it looks like this. And it's in compression, so the force is this way. Because all the truss members are two force members, and this little thing that we have, a free body diagram, qualifies as a truss. It has, we're ignoring the member weight, all of the forces are applied at joints, and the members are connected by frictionless pins, and all the rules, assumptions that we made for a truss, it qualifies as. It just has this different thing that there are two pins supporting it instead of a pin and a roller. But when I look at G, the only reactions, the only forces at G are in this horizontal line. And it doesn't matter that it's horizontal, it just matters that they're in a line. So that means the pin at G, the pin over here, has to have the equal magnitude but opposite direction reaction. So it either has to have one of these things, and I'm not drawing the actual pin like the bolt or whatever, but if you could look at the bolt if you wanted to, that's holding G to this little triangular thing. But so this pin, even though normally pins have X and Y reactions, this one I can model with a single reaction. So it still have the three external reactions, two at the other pin, the one at E, and one reaction at G, which in this case is horizontal. Now, it wouldn't really matter if GH was at some angle or horizontal. I know that since there's only one member connected to G, member GH is the only thing connected there, that the reaction of the pin is going to be in that same direction, because the reaction has to be equal magnitude to the force in G, because that's the only thing connected there. So knowing that, when I draw the free body diagram of the truss, let's move this down, we don't need that quite yet. I've got the whole truss, I've got the thing like this. I don't know, remember what it looks like, but oops, kind of missed. Whatever it looks like, I have the EX and EY, but over here, and I guess I could draw this member too, GH, I have G, I could call it X in this case because it's horizontal, but it doesn't matter what I name it. And then I've got whatever forces were on the truss. And so I still end up with three reactions. I can do my normal process, do moments about E and find G, GX, and then do summation of forces in X and summation of forces in Y, get all my external reactions, and then I don't even know what the problem's asking for. It's asking for everything. So one of the, no? Oh yeah, it does. So that's for everything. And not only does it ask for every member force, but it asks for the required diameter. So these are all rods, and you have different forces in them. So you're basing that on stress. Once you find the diameter, then how long did it change? So this one's definitely set up to, Excel or MathCAD or something, or a whole bunch of calculating going on. Obviously, on an exam, this is not an exam problem. An exam problem would be, given this, find if it's a simple truss, then find the force in member CD. And it's intended to be a method of sections problem, and you don't even find the reactions. You just cut the thing through CD, CH, and HI, and use the left-hand side of the thing to find the reactions. Or to find not the reactions, the force in CD. If it's a medium or hard level problem, then it's find the change in length in CD, or the stress in CD, axial stress in CD. Or maybe it's the pin at C has a diameter or material strength, and what's the necessary diameter. In that case, you have to figure out what's the largest force on it and design for that. Something like that would make it a harder problem. More straightforward, it's just what's the force in there, but it doesn't tell you that you need to use the method of sections or use the method of joints. another way this same problem could be intended to be a really simple problem is find the force of member AJ. In that case, you can make it complicated by finding the reactions at E and G and then working your way across method of joints to get to A. But what you should do, if I asked you to find the member force in AJ, is just immediately draw the free body diagram of joint A. You know what force 1 is. You know the angle that AJ is at, and do a 2D concurrent force system at A, method of joints, at A without doing anything else. And so it's like a one equation problem. So you could, if you don't understand what method of joints is doing and what method of section is doing, and you're just following my little step 1, draw the free body diagram, step 2, find the reactions of the whole truss, and then do all this other stuff, then this problem could take you 10 minutes to do, working your way from one end all the way over to A to get to method of joints. But if you can see what's going on, then this is a 1-minute problem or less. You write summation of forces in the y direction at joint A and you have your answer. So you kind of need to spend enough time with these before the exam to make sure that you can see the best way, because it does start to add up. If you do every problem the longest possible route, you still get the correct answer, but it took you forever to do that, and you have 110 minutes to do all of the test. So that's what I'm going to say about that one. And then I think we'll talk about centroids. So centroids, again, that's the last topic on the exam, so it's something we haven't talked about yet, but it is, let's clear out some space here, centroids. So this is a cross-sectional area property. So the different things that we're headed into, we're headed into the middle section of the course where we're talking about flexure. So things are bending now. And when we want to talk about things bending, then we need to deal with their cross-sectional shape. These trusses, I guess you've kind of dealt with the cross-sectional shape in the sense that that problem we just looked at asked you to calculate the stress in the member, so you had to know if it was a circle or a square or whatever. You had to know its area. But now we need to know a little bit more about the cross-section in order to do what we need to do next, which is flexural stress. And so this idea of a centroid is sort of like the, I'm going to say center of mass, but I'm going to put mass in quotation marks because we're going to talk about a planar cross-section. So this cross-section, we're going to start talking about beams and things like that, and a beam, you know, a beam could be a rectangle, like a 2x4, and, you know, it goes off somewhere, and its cross-section is just this rectangle. A beam could be an I-beam, so it has a cross-section that kind of looks like the capital letter I, and it goes off somewhere. More complicated to do, but its cross-section is this I, and yes, you could make a beam that on one end looked like a rectangle, and at the other end of the beam it was a circle or, you know, some other shape, and it changes shape throughout the length of the beam. And yes, you could make a beam that at one end is made of wood and the other end is made of steel or whatever. You know, it could transition to different materials. Those are not normal, and they're not normally what you're going to deal with when you're, and they're not what we're going to deal with when we're talking about beams and flexural stress. We're going to assume that the beams and the things that we're building stuff out of pretty much have one cross-section from one end of the beam all the way to the other end of the beam. They don't change from a rectangle to an I-beam halfway through, or they don't change from aluminum to steel halfway through. They're the same material and the same cross-section from one end of the beam to the other. So we're going to assume that the beams that we're dealing with maintain their cross-sectional area, and not just the area, but the shape also. So a rectangle stays a rectangle and it stays the same size. And material properties, so we don't go from steel to aluminum. From one end of the beam to all the way to the other. As long as we assume that, which is a good assumption, you don't normally make beams that change from one end to the other, although you could, you know, if you're doing some really sophisticated, fancy, or just artistic design, then yes, they could change from one to the other and whatever. But for what we're doing, they're not going to change. That in general, most all the time, the beam is not going to change. And I'm not talking about a change where you drilled a hole in it to bolt something together or whatever. That's not the kind of change. I mean literally changing from one shape to another shape, or one material to another material. As long as we assume those, then we can talk about this centroid being the center of mass of this plane. And we're going to just deal with the cross-sectional area as the rectangle or the eye or the circle or whatever it happens to be. We can just look at that and kind of summarize or generalize the beam into just that shape. So one of the things we need to know is, where is this center of mass? So that's really easy to do when the centroid, or when the shape is a rectangle. You know, if our shape is a rectangle, then the center of mass is literally in the center of it. You take the height and divide by 2, you take the width and divide by 2, and this little location, I'm going to call this location the centroid, and I'm going to give it coordinates x sub c, y sub c. So if I was measuring the x-axis and the y-axis from that bottom corner, then this distance is the one I would call x sub c, and that distance is the one I would call y sub c. And the little c subscript means centroid, and x means the distance in the x direction from the origin, and y means the distance in the y direction from the origin. And so that's really easy for here, for a rectangle. X sub c equals base over 2, and y sub c equals height over 2. Right? That should be intuitive. If it was a circle, same kind of thing. It's just the diameter over 2. You know, it's right at the very center. It gets more complicated. Yeah, well, even the I-beam is symmetric, so it's right in the middle. But when things are not symmetric, that's when we have a little more issue in figuring it out. So another type of beam that's relatively common is, instead of an I-beam, a T-beam. So it has a cross section that looks like the letter T, or a capital T. Here, if I put my origin, let's put my origin right here. So there's the x-axis, and since I have symmetry about this one, you know, it's bilaterally symmetrical about the y-axis, I'll put it right there in the middle. The way I've drawn it, x sub c is obvious, I hope. X sub c equals 0 because of where I put the origin. But y sub c I don't really know. Y sub c is, you know, it's right here. But I don't know what this distance really is. And so I need a way to calculate that distance. And that's what we're going to do. Is there is an integral method. So if we have the equation of this beam, you know, the shape that creates the beam, you have some equation for that, then there is a way to integrate. I'm not going to cover that in class. I'll cover that and put it just out there for you to watch if you want to, because there is a way to do that. And I think there's one of your Weber problems, maybe 2, that have you do that. But what we're going to do is, most beams are made up of a couple of primitive shapes, like rectangles and circles and triangles and things like that, and you get charts like this that have 4, a triangle, a half circle, quarter circle, and they put a rectangle. I don't know why they put a rectangle, but they did put a rectangle on there. And then in your note reference material for the exams, there's 2 or 3 others. There's a spandrel that's kind of like a parabola type shape, and maybe there's an ellipse in there, stuff like that. But most of your beams, like this T, is just 2 rectangles stuck together, one across the top and one in the stem part. And so we can take this idea of, well, I know how to deal with a rectangle, and just how do I deal with 2 rectangles? So that's what we're going to do, is how do we combine these primitive shapes into complex shapes. So to do that, let's take a little bit of a detour into maybe a thought experiment type thing. Where I've got a coordinate system, and I've got some weights out here. You know, they have 3 different little pieces. Doesn't matter how many, just 3 is the number I wanted to deal with. They each have their own little weight, and they each have their own position measured from the origin. So this one is 1, 1, and this one is 4, 4, and this one is what is that? 1, 2, 3, 4, 6, 1. You know, I can plot them if I wanted to. And they each have their different weights. Weight 1 is, I don't know. Weight 1 is, let's do some 4 pounds. Let's make this one 3 pounds. And let's make this one 5 pounds. So they're different weights. Doesn't matter that they're different weights, they're just different weights. And different weights, different locations. And these could be like this. You know, here I have 2 rectangles, they happen to be touching one another. Here I have 3 circles, they're not touching one another. So I'm making a more general case here with the circles versus a specific case of 2 rectangles shaped like a T. So if I wanted to find the centroid of these 3 groups, or 3 pieces, that don't happen to be touching one another the way I drew it, it would be the same process as finding the centroid of 2 rectangles that are touching one another. So the centroid, I said, is basically like the center of mass. Now, I extrapolated away all of the mass part of it, so I'm not worried about density of the material because I said that the density doesn't change. Actually, I just said the material doesn't change, which implied the density doesn't change from one end to the other. And I said that the cross-section doesn't change from one end to the other, so I don't have to worry about it getting bigger or smaller from one end of the beam to the other end of the beam. So I'm really only looking at areas. And here I've got weights, but these weights could also be just the area, and assume that the density doesn't change and the size doesn't change and all that kind of stuff. But for now, it'll make more sense using weights because they're forces.
Okay, so like why aren't, like how you did your like graph thing, why is 6, 1 lower than 1, 1? I need to look into that.
Oh, that's not 1, 1, that's 2, 2. That's why, because I wrote the wrong thing. There we go. And that one is 1, 2, 3, 4, 1, 2, 3. All right. So yeah, now that makes sense. All right. So what we're going to do is we're going to say that the center of this somewhere, the centroid, which is, you know, sometimes it's the actual center, right? But other times we're actually talking about kind of like for this T shape. If I cut that T shape out of a piece of cardboard and laid it down flat, I should be able to balance, you know, theoretically, balance the T at the centroid. So if I took a rectangular sheet and put a point at the very middle of it, I should be able to balance the rectangular sheet. Should be able to do the same thing for the T shape at its centroid. So it's kind of like there's some point out here in my group. Let's make it different. You know, I assume it's somewhere right there. I don't know exactly where, but somewhere right there. And if I were to add up all of the weights, so this is the total weight, then that blue point is the centroid, where if I collapsed all the weight to that one point, it would all balance right there. And I can write an equation that tells me this. Basically, I could say that if I add up all of the, and I'm going to call them moments, although they're not really, I guess maybe if you look at this as you're looking down on the XY plane and these weights are actually going down into the screen, not the way I drew them, but they're, you know, I'm looking at it flat and these weights are creating a moment about the x-axis, then maybe you could make sense of that. But each one of these weights, so W1, has some distance. In this case, let's find out how far they are in the x direction. So I need to measure how far they are from my reference. My reference is here, and the reference can move. You can put it wherever you want because you're measuring everything from the same reference point. Here I picked a spot. Here on this T, I put the reference kind of in the middle at the bottom. Here on the rectangle, I put it in the bottom left corner. So the reference is not set, except when you're solving a web word problem or a test problem, there'll be an origin that you have to measure everything from. All right, so if I'm trying to figure out how far over, I want to know this distance. That's what I've called x sub c, the x coordinate of the centroid. I want to know that. Then the x coordinate of that centroid should have the same effect as every one of these individual ones summed together. So W1 times its, or Wi times, let's do ones, plus W2 times how far it is from the y-axis, plus W3 times how far it is. And we could generalize that to the summation of Wi times xy. So I could have thousands of these little circles drawn out there, and I could add them all up and figure out how much each one weighs, how far is it from the y-axis, and that's kind of like a moment. It's a force times a distance in this case. So that's kind of like I'm adding up all of the individual moments. Those have to equal the total weight. So the blue dot is the summation of all the weights together, and it has some distance from the y-axis, same place I measured all these x1, x2, x3s. Those two moments, the summation of moments on the left-hand side of the equal sign, and the total weight times however far it needs to be from the y-axis, those should be the same thing. So basically, I'm just saying that I want to replace all of the circles, the black circles, with one blue circle. So I add up all the weights and figure out where to put it to have the same effect of all these individual ones. And then I can just solve this equation. X sub c equals summation of all of the individual weights times their individual distances divided by the total weight. And in this case, I can actually put all the numbers in. It would be, so weight 1, I said, is 4 pounds, and it is 2 feet, maybe, plus weight 3 is 3 pounds, and it is 4 feet from the y-axis. I'm measuring everything in the same direction. And then the third one, I made 5 pounds, and I made it 6 feet. So those 3 moments need to have the same effect as the total weight, which would be 4 pounds plus 3 pounds plus 5 pounds times that distance I'm looking for. So let's see. So I get 8 plus 12 plus 30 divided by 12. 4.17. And the units I'm using here are feet. So I kind of drew it in the right spot. I was off a little bit. It should have been over to the right a little bit from there. We could do the same thing for y. We could do all the y directions. W1 times 2, W2 times 4, W3 times 1, and they need to all create the same effect as this blue total weight that I've drawn kind of a little more than 2 feet above the x-axis. So I can do the same thing for y. So this is the process I want to do. I want to generalize it because I'm not dealing with weights, I'm dealing with areas here. So this is the area of 2 rectangles when I talk about the T beam, or the area of a single rectangle with the one there. So like I said, we're going to assume that the density doesn't change, the cross-sectional shape doesn't change, and so this weight is going to just be represented by an area. So I'm going to use the equation or equations that x sub c is the summation of each area times their individual x coordinate divided by the total area. This term in the numerator, this is called the first, and I'm going to put it in quotes, moment of area. So it's a moment like we calculated this other one where you had a force times a distance, but we've generalized this shape to not really be a force. It's just an area that represents a volume that has a weight that would create a force. So this numerator is called the first moment of area. First because it's a first order equation, one term times another term. There's a second moment of area that we'll do later that has a squared term in there. And then the total area on the bottom. And I could have a very similar equation for y sub c. The only difference would be I would sum up the areas times their individual y coordinates and still divide by the total area. And like I said, you can, let's put them over here, x sub c, you can use an integral form, x dA over the integral of dA. So the integral of dA is just the total area. X dA, integral of x dA is the x coordinate times the area, but the area is, you know, a differential area. And you can do the same thing for y. And you can do z also. We're not going to deal with z in this class. Whoops, dA. And like I said, I'll do these just a little separate video of their own, or maybe we'll do them tomorrow. It depends on how far we get with today. There's not going to be one of these on the exam. There's some on the web work. All right, so I need to take this idea and apply it to something like this T. So let's take a very, this is about as simple without just being one you look up in the chart here as we can get. So let's draw our T shape. Let's make it a little bigger. All right. So, and I'm going to, you know, make this into part 1 and part 2. We'll put the x-axis here. Since we do have symmetry, let's put the y-axis right down that line of symmetry so that we don't have to worry about calculating where x sub c should be. It's just going to be somewhere on that y-axis. We just need to know how high up it is, and so we need to calculate y sub c. Let's put dimensions on here. Let's make this 1 here. Let's make this one 1, 2, 3, 4, 5, 6, and then well, we could probably move it down a little bit. Oh, I lost part of the y. This one 1, 2, 3, 4, 5, 6, 7 across here, and well, 1 for this distance. All right. So what I like to do is go in, and this is going to be a very thorough process. You could directly plug things into these equations, particularly when there's only 2 pieces. You won't get very confused with 2 pieces. they'll get to have more pieces as we go, but I'm going to do the full like bookkeeping method for this. And what I like to start with is I've already actually kind of started because I've divided it into two shapes that I have equations for. So there's a rectangle at the bottom. I don't really need to look up the equation for a rectangle, but it does tell me that the centroid is located at half of the base and half of the height. And it even gives me the area for a rectangle, if for some reason I didn't know that. All right, so the first thing after dividing it into the primitive shapes is I want to go in and mark where the centroid of each part is. So there's where I think the centroid of part 1 is, and there's the centroid of part 2. And each one of those has their own, and both of those lined up on the y-axis, which also shows me, again, that x sub c, by observation, x sub c equals 0. So I already know that. I just need to know what is y sub c. I usually go in and try to mark where I think y sub c roughly is. You know, and I know it should be somewhere like that. And that'll kind of help me figure out when I calculate the numbers that did I do something wrong or not. I know it should be somewhere there. If I cut this little T-shape out of a flat piece of foam core and tried to balance it, I'd have to put the peg I was balancing on somewhere near where I drew that circle with the X in it. All right, so here's the bookkeeping method. What I do is I create a little, kind of like Excel sheet. I don't think I would actually do this in Excel because it, it hides a lot of what you're doing in the cells. That's hard to track down, but well, I think I might have said X sub C. This is Y sub C. So the XC is the X coordinate of this point. So the ordered pair for this would be XC, comma, Y sub C. And since I put the origin where I did, the X coordinate of that point is 0. And the Y coordinate, I don't know. So I'm still labeling it as Y sub C. It won't always work out that way. Sometimes you'll have parts. In fact, the next one we'll do, it won't be symmetric, so we will have to find both X and Y. This one, we're just simplifying it. So I make a little chart that has part 1 and part 2. And I know I need these things in the chart. I need to know the area of each part. I need to know the total area. I need to know I don't need to know the X coordinate because for this particular one, because I've already decided where X sub C is at 0, but I need to know the Y coordinate of all the centroids. And then I need to multiply the area times the Y coordinate to get this numerator. So first thing I do is area. And these are, I guess, inches, so we'll make these in square inches. Part 1 has 7 times 1, so it's 7. Part 2 is 6 times 1 is 6. All right. The Y coordinate of each part is just going to be measured in inches. These are all going to be measured from the origin, so they all start at the bottom and go upwards. So part 1, I am measuring this distance. This is Y1. Y1. So it is 6 to get to the bottom of part 1 plus 1/2. So it is 6.5 inches. Part 2 is this height, which is half of 6, so it's just 3 inches. And then the equation I'm trying to solve is this guy. Y sub C equals the summation of the individual area times the individual coordinate of each part divided by the total area. So I need to construct this numerator, which means I need to take all the areas and multiply times their Y coordinate. So 7 times 6 hold on. Get my calculator in the right mode. 7 times 6.5 is 45.5. So this is going to be A times Y. It'll give me units of inches cubed. It's not a volume though. And then 6 times 3 is 18. And then if I add this column up, that will be the summation of all the A times Y's. So 45.5 plus 18 is 63.5. And then they had units of inches cubed. If I sum this total, that'll be the total area, so 13. Then I just plug in these numbers, 63.5 inches cubed over, these are inches squared because they're an area. And I'll get, let's see, 4.88 units of inches. And then I go back to my chart over here, and I kind of drew it in the right spot. I drew it at 1, 2, 3, 4, 5, more or less, and it's 4.88. So I can be convinced that 4.88 is the location of the y coordinate for this centroid. That makes sense. If I were to cut this T-shape out, draw a mark that's in the middle on the y-axis and 4.88 inches from the bottom of the stem, I'd be pretty close to being able to balance it right there, assuming it was perfectly flat and all that kind of stuff. So that's kind of the simplest one we can do that's not straight up read it out of the chart. Any questions with that before we do one that's a tiny bit more complicated, but not a lot more? All right, let's do one that's a little bit more. This one we'll need to look at the chart until we memorize these things. And this chart is available on the exams. You don't have to memorize them all. You just do them enough that you probably will memorize them, but you don't have to. The chart's available. All right, this one is, let's see, I'm going to get 2 by 3, this shape. So this is a beam that, you know, kind of looks like this, and there's its cross section. Not a normal beam that you're going to put in a building, but it'll help us do some new things with our equations. So let's put the origin for this thing, let's put it here. So here's the x-axis, here's the y-axis. If you were just doing this on your own, you can put x and y wherever you want to, but since you're trying to plug these numbers into WebWork or in a multiple choice answer on an exam, you kind of need to use the reference that I give you, otherwise your numbers won't match that origin. To me, this looks like 2 parts, a rectangle and a triangle that are shoved together. Let's put this as 2, whatever the units are. This one will be 3, and this will be 4. All right. Following my little thing I did last time, I know the rectangle is right in the middle. That's where its centroid would be. The triangle is a little bit harder to figure out, but I'm going to put it, you know, right here. I know that it would be somewhere near that larger, fatter end of the triangle versus closer to the pointy end. So I'm going to put it right there. And then I'll have to look in the chart. So, whoa, went too far. Look in the charts to kind of figure out where it really is. I just want to know, you know, roughly where is it at. So the whole shape looks like it should be, you know, right in here somewhere. Oh, well, let's actually draw it as the circle with the X in it to make it different. So that's where the whole centroid should be, somewhere in there. All right. So let's make our little, and I'll call this part 1 and the triangle part 2. So here's my part number. Sometimes I even draw the little picture of them to remind me what they look like, so I don't get confused. Area in square inches, 8 for the rectangle, and 6, don't forget to divide by 2 for the triangle, so 4 times 3 divided by 2. This one, I don't know where X or Y, so I need to do both of them here. So let's do X first. So X for the rectangle is at 1, I know that. X for the triangle, this is the distance we're talking about. X1, or X2 actually, because this is part 2. is that distance, measured from the y-axis, the reference axis, in the x direction over to the centroid of part 2. I drew it, and it looks like it's 2 to get all the way through the rectangle plus some distance into the triangle. So I need to look at my chart. Fortunately, this chart has the triangle oriented, it's really cluttery, but it's oriented in the exact same orientation that the triangle is in my picture. Now it looks like it's kind of maybe shaped differently, but it's oriented the same, where the right angle is at the bottom left corner versus a triangle that's like that, you know. All right, and it has this thing, it's calling it X bar. That is the thing I've been calling X sub C. And it says that X bar is the base, which they have labeled as the bottom of the triangle, divided by 3. So if I take that piece of information and go back up here, the bottom of my triangle is 3. So this distance that they have labeled right here as X bar should be 3 over 3. That is not the number I want in my chart, though, because I've got to measure everything from the y-axis. So I have to add 2 plus 3 over 3, which is 1. So x2, the x location of the centroid of part 2, is actually 3. 2 plus 1. Now I could go and do the a times x right now, I guess. A times x in inches cubed. And I've got 8 times 1, and I've got 6 times 3. I've got 26 total here, and 14 total there. So I can solve for x sub c. So x centroid is 26 inches cubed over 14 inches cubed. Or inches squared, that's total area. Okay. Oops. 1.86 inches. And then I look at where I drew it pretty much right at 2. So 1.86 is close to 2. I just kind of randomly picked where I thought it would be. I can be convinced that 1.86 is correct. I didn't calculate some number like 10, which would not make sense. All right. Then I keep going with my chart, and I do y for each piece. So the y coordinate of part 1 is 2, measured from the x-axis, 2 inches above the x-axis. For part 1, I need to consult my chart. Now they want what they've labeled as y bar right here. That diagram is showing me that y measured from the bottom x, what they have is the x-axis, which may not always be my x-axis. I might have to, you know, orient these things different directions to match what I've drawn. But in this case, it's the same. It says y bar is h, so the height over 3. So it turns out that for a triangle, the centroid of a triangle is 1/3 of the base away and 1/3 of the height away from the right, well, they're not always right angles, but from the larger end of the triangle. So the height is 4, so that's not easy. I should have made that 6 or something, I guess, but I didn't. So 4/3. Oh, that's not what I want to add. No. I want to now multiply a times y, and a is area, y for part 1 is 2, so 16. 6 times 4/3 for part 2 is 8. So I've got 16 plus 8 is 24. Y sub c is that 24 inches cubed. Same total area, 14 inches squared. So 24 divided by 14 is 1.71. I kind of drew it at 1.5 or so. So I could also be convinced that that's a reasonable number. So I would have the X and Y coordinates of the centroid for this wedge sort of shaped beam, or beam has a wedge shaped cross section. Yeah.
So what is that stuff? What's that green stuff that's underneath where like the centroid thing is? What does that say? Like the X.
That was just the time I labeled X2, so that in that particular case, what you read from the chart is that here you go to a triangle, X is B over 3. But that is not what goes into the equation, because X2, the thing you actually want to put into the equation, is measured all the way from the y-axis, which you can't see on this picture, but the y-axis goes all the way to the left edge of this part. So you have to not just read directly from the chart. So don't just put base over 3, so 3 over 3, and that as your answer. You need to go all the way back to your reference axis. So you need to actually put 2 plus the base over 3. So you needed to put a 3 in the chart, not just 1. Basically, the point there is that, yes, you have these charts that have numbers in them, but sometimes you have to modify these numbers to match what you've drawn, because they're not the same orientation as what the part you're dealing with is, or they're not in the same reference system. So here they show where X and Y are on these 4 pictures. That may not be where X and Y is on your picture. So don't blindly follow the chart. In fact, let's do one where you can't blindly follow the chart. All right, here's one. I made this one like, and I did this. Oh, wait, that's not how I did it. It's got a little notch in it, and the origin is here. All right. So this one is 3 parts, the way I would do it. I would do part 1 is this rectangle, part 2 is this triangle, and part 3 is actually a negative part. It's like a cut out half circle. But it's still a part, I just have to cut it out of there. Make it a little bigger. All right. And then we need some units and things. 3, 2, don't want to put that there. This will be 1, this will be 2, and this will be 1. Okay. See if we can make our circle a little bit more. All right. More better. All right.
1, 2, 3, like the.
Oh, the part numbers. Yeah, I put the rectangle as 1, the triangle as 2, and the half circle as 3. So in fact, let's do that over here. Actually, let's do it underneath it so that we don't run out of room. 1 is going to, and this is why I sometimes draw the little pictures. 2 is this triangle, and 3 is this little negative half circle. They each have an area. That shouldn't be any new thing. The area of the rectangle is, it has a base of 3 and a height of 4, so 12. You're not worried about that something's cut out of the rectangle yet. We're going to cut out the half circle from the rectangle when we give the half circle a negative area. So that's how we're going to deal with that. Right now, part 1 is an entire rectangle, because that's what's in here, is an entire rectangle. Part 2 is this triangle. It has a base of 2, a height of 4, so 8, but divided by 2 is 4. And then here we have a half of a circle. It has radius 1 or diameter 2, whichever way you want to go. So pi would be the area of the whole circle, but pi over 2 is the area of a half circle, and it needs a negative sign because it's actually a whole. It's not a thing that we're adding, we want to subtract it. So if I add these up, they will be the total area. So 16 minus pi over 2. 10.19. We'll have to start rounding a little. That's the total area. All right. Let's draw in where I think the centroids are. For the rectangle, the centroid's pretty easy. The triangle, I remember that it's a third away from the fatter end of the triangle, so it's going to be up here somewhere. The semicircle, it's somewhere right there. I could, if I wasn't sure where it was, you know, they kind of show it right here on number 2 across there, that it's not in the exact middle, but somewhere. All right. Now, this one has the origin kind of in the middle of the part, which is fine. That might be on the web work or on an exam, or maybe where you want to put one. That might be where it ends up at. Now, there's nothing stopping you from saying, I really don't like the origin being in the middle of the part right there. I want to move it to the bottom left-hand corner. As long as you remember that after you're done calculating, you got to translate your numbers that you got measured from the bottom left corner back to the numbers that would be measured from wherever the origin's actually given. So I wouldn't really recommend moving the origin around unless you really don't want to deal with it wherever it's given. Because chances are you'll forget that, oh, well, I forgot to move it back to where it's supposed to be. Or at least supposed to be as far as the problem is concerned. All right, let's do x. Right off the bat, it gets weird because the x coordinate of part 1 is actually in the negative direction. So I need to specify exactly where this is. So this is 2 inches, and so is this. Okay. So it turns out that the x coordinate of part 1's centroid, so dot right here, this is 2, that's 3, that is negative 0.5 inches. So you'd have to go through, it's the base of this rectangle is 3 inches, so the centroid is 1.5 inches over from the edge. The edge is 2 inches over to the origin, and you got to count backwards. So you got to be very thorough in this distance right here is that distance there. So those match up. So there's lots of little pieces where if you're not careful, then you can make a tiny error and it will be hard to track down later. Part 2 is on the right-hand side. So that's good. It's like we've been doing. It is a triangle. And if I look here, my triangle is drawn like this, which is the one I've got in the chart, but it's rotated 90 degrees clockwise, right? So I have to take that into account. So technically, if I want to think of it that way, the dimension I'm looking at on this chart is labeled y bar because I have to rotate it to make it match up. And for a triangle, that's not a big deal because x bar and y bar are both whatever that dimension is divided by 3, so that's not a big deal. So I wouldn't technically get that messed up. So the chart tells me this dimension is 2/3. I'm measuring from the y-axis though, so I've got to add in 1, this one, plus 2/3. So 1.67 inches. The semicircle, so back to on the left-hand side of the y-axis, so it's a negative x. And it is in the chart, oh, come on, there we go. You know, it's shown laying down flat. Mine is this way. So the dimension I want to know is how far is that? You know, there's this little centroid. How far is that little green line? So again, it's rotated 90 degrees. In here, they've only got y bar shown, but that is the dimension I'm interested in. So they say that y bar is, if we scroll over, it's 4r over 3 pi. Yes, 4r over 3 pi. So that on my picture is that little distance. What I really want to know is 2 minus y bar. So that's what they have as y bar. But I want this distance. This would be, well, they labeled it y bar. I'm using it in the x direction though. So that's y bar is from the chart, not actually in the y direction. I want this distance, x, this is part 3. So that's going to be 2 minus what they have as y bar. All right. So 2, and it's all negative because it's to the left of the negative sign. So negative 2 minus 4, the radius of the circle is 1 over 3 pi. So this equation is 4r over 3 pi, and that's a thing that you wouldn't know where's the centroid of a semicircle, like you would know where the centroid of a rectangle is. So you probably have to go look that up. All right, let's get it back up here. Let's see what that number is. I don't know. 4 times 1 divided by 3 divided by pi, 2 minus that number, and negative. So that number is actually negative 1.58. So this whole number, put it over here, negative 1.58. So that one has lots of chances to make a mistake. Maybe you forget that it's negative, maybe you forget that it's 2 minus 4r over 3 pi, or whatever. And that's why I like the bookkeeping method here versus just throwing all these numbers into the equations. You know, you'd throw everything into a big long line of an equation in the numerator and divide by the total area and get these things. There's a lot of chances to make mistakes doing that. So this is a little less chance of making a mistake. Let's do our a times x column. So the area of part 1 is 12. It does have a negative x coordinate though. So I have a negative a times x. I have to keep track of the negative signs. So negative 6. The next one has 2 positives, so 4 times 1.67, 6.68. And then this one has a negative area and a negative x coordinate. So that is going to be a positive term here, so pi over 2 times, they're practically the same number, 1.58, 2.48, and it is positive. What's happening here is, you know, I'm trying to figure out where the x coordinate is. So if I cut away material that's on the negative side of the y-axis, then that does shift the coordinate of the whole centroid to the right, towards the positive side, right? So I have a negative area on the negative side of the y-axis, shifts the centroid of the whole shape to the right by creating a positive term in this summation of ax, which is 2.48 plus 6.68 minus 6, 3.16 inches cubed. All right, so then I could go in and x sub c is, that's a point, not 316, 3.16 divided by 10.19 inches squared. So 3.16 divided by 10.19 is 0.31. So it is telling me that slightly to the right of the y-axis is the centroid of the whole shape. So somewhere, well, we didn't even draw it in, but somewhere right in there. To get y, we do a similar thing. We go and find the y-coordinate of everything. Now the y-coordinate for part 1 is on the x-axis, so it's 0. The y-coordinate for part 3 is on the x-axis, so it's 0. So the only thing trying to move the centroid above the x-axis is the fact that the triangle has more mass, and again, mass is area here, so it has more area above the x-axis than it does below the x-axis. So it has a, I'm trying to get that distance right there, y3. This one can be a little bit tricky because I go to my chart, my triangle, it says that y, well, in this case I've rotated 90 degrees, so it's labeled as x. X bar is base over 3. The tricky part is to not forget that what it's telling me is this distance. That is x bar from the chart. And I want y3, which is measured down from the x-axis. So I need to take 3, this total height from the center of the part up to the top of the triangle, 3 minus this x bar number that they've given me. So I would actually put in 3 minus x bar is the, in this case, height of the things, which is 4 over 3. So 3 minus 4/3. 1.67. So, or 6.8, no, 6.7. So 0 plus 1.67 plus 0, the total is 1.67 inches. Oh no, I'm not done yet. I have to multiply these together. A times y, y is 0, y is 0 down here. Area here for the triangle is 4. 4 times 1.67 is 6.68. So the total of this is 6.68 inches cubed, and I can do y sub c is 6.68 inches cubed divided by the total area of 10.19 inches squared is 0.66. So the triangle is able to pull the centroid up a tiny bit. You know, it's more like, oops, wanted the whole thing. More like up there. So that's kind of where the centroid of all the shapes are. Now, oh, go ahead.
How did you get 3 minus the...
Oh, okay, so 3, so it's, again, I have to measure from the x-axis, and so the piece of information they give me is this. That's from the chart. I want this one, y3. So the 3 is this height. Oh no, this is supposed to be 2. Oh shoot. Well, so slight problem. This right here, this number is a 2. Let's fix it. Which makes this number 2 minus 4/3, 0.66. 2.67, which makes this number 0.67 times 4, 2.67, which changes this number, which changes this number, divided by 10.19 is 0.26, which now we're back to, we almost drew it in the right place to begin with. This thing really does go somewhere down there, and that part too. There. Right, so yes, 2 for that. I looked at 2 plus 1 over here on the side, but it's only 2 total. Not 2 plus 1, it's 1 plus 1. See, very easy to make mistakes in these things. So this one's on the level of what a medium or even kind of hard, but not really hard, but most of the hardness of this one is just all the little numbers you got to keep track of. But it's on the medium level. This one, and this one are both on the kind of the easy level of centroids. And this one would be more on the medium-ish level of centroid problem. So there'll be probably something like this on the exam. I don't know if it'll have this many different little features to it with the negative x and the negative area, but it could. Those are all things that could show up on the exam. And then you'll also have one that's more like this, where you're adding two things together, kind of normal. Yep. They'll still have. Okay. Mm-hmm. Yes, which I may or may not have done correctly. Oh yeah, that doesn't seem right, does it? I think if I could go back in my clock here, I probably did pi plus 2 or something. So yeah, so this little number, see how easy it is? 14.43 inches squared. So what that does, those numbers, 14.43 inches squared. So it makes these even smaller numbers. It wouldn't change anything else though. 0.21 and 0.18. Inches. I put no units on that, inches. So yeah, they are even closer to the origin, and it's totally possible that they come out to be 0, depending on where you put the origin. If you put the origin in the direct center of a rectangle, x and y will both be 0. Here, they are slightly to the right and above the origin, and only because of the triangle having more area above the y-axis. And basically, the triangle has area that's similar to the negative area subtracted by the semicircle. Not the same, but on the same scale of area. So yeah, that little issue needs to be fixed. Okay. I think that'll get us straightforward examples, one that has lots of little things. Make sure you calculate your numbers twice. Maybe I only did 12. I don't know what I did there, but to get the 10.19. But yeah, if we were to subtract off pi over 2. Yeah, no, the area should be pi r squared. The radius is 1, so that's just pi. And it's only half a circle, so divided by 2, and it's negative. So I put something wrong in the calculator. Not exactly sure what it was.